Hey class, welcome back, and we're going to take a look at writing out a skeleton equation for this particular problem, looking at different aspects of it and like classifying it, figuring out what type it is, and then we're also going to balance this, balance the equation we get from this reaction. And there's various ways to do this. This method I'm going to show you is one that I feel is useful, that no matter which type of reaction you're trying to balance will work. You'll see different people, different textbooks show you multiple techniques. They're all basically the same thing. I've just found some are a little more intuitive than others. So just with that, let's just jump in here. Let me show you what I think works really well. So first and foremost, no matter what, you're always going to have to be able to name or write the compound formulas for the names. Well, you see calcium chloride is here, potassium phosphate is here. You've got something that says the chloride product, all right? So you got to figure out what that is, and the phosphate compound formed. So reading this, we see that there's going to be four things here that we're four compounds that we're going to have to put together. So let's get started let's just start from the reactants and move forward. So when calcium chloride and potassium phosphate are dissolved in water, they react. So this first sentence tells us that calcium chloride, potassium phosphate, they're going to react when they're mixed in water. All right, so let's do this. We know calcium chloride. We know calcium is a +2, and then chlorine is that -1. So this is scratch work that we're doing off to the side somewhere. So we can see that we're going to need 2 chloride ions and 1 calcium. So we know we're going to get CaCl2. All right. And then let me go ahead and erase this, get this out of the way. This is our scratch work. And then plus the potassium phosphate. So remember, potassium is a positive, right? Potassium. And then phosphate, remember PO4 3-. Now, until you're sure of all this, remember, you always go back to two things, your periodic table and your reference sheet. So if we go back to the periodic table, then we see right here where potassium is, right? And then we just move all the way up here and we see that potassium has that +1 oxidation charge. We're good to go. We go to our chemical equation sheet, and what we notice is right here where our polyatomic ions are, we just want to find phosphate. And so if we zoom in, right there is phosphate, PO4 3-. So that's where I got that from. So nothing to memorize. After you write these enough, you'll just remember them automatically like anything, just like writing your name, whatever the case might be. But until that time, what you want to be able to do is reference this. So in class, we'll pretty much use this sheet very often, but you can always look these up online, et cetera, et cetera, et cetera. So that's where we got the 3- from. So with that said, again, we're looking at the charges, right? And so that means we're going to need a total of 3 potassiums because we need the charges to equal 0, remember? So that's in a previous lesson. So if you've forgotten, you're going to want to go watch those videos on how to write ionic compounds. All right. So that's K3PO4 because we only need 1 phosphate. All right. There's a reaction, so I'm going to write an arrow. Let me get rid of this. All right, and then the chloride product remains in aqueous phase while the phosphate compound formed is a powder. So let's go ahead and address these terms right here. These two reactants, remember, these are your reactants. Everything on this side of the arrow are reactants. It says that they are dissolved in water. So what we do is we denote that by writing AQ, and we put it in parentheses, and what this means is aqueous. And aqueous just simply means that it's been dissolved. And usually it means dissolved in water. It usually means that. But sometimes these things are dissolved in like alcohols or oils. I mean, an aqueous solution just means the substance is dissolved. Okay? So keep that in mind. All right. And then there will be other other, and we call these things phase labels, all right, before I forget. All right, and I'll talk about this in multiple lessons, but I'll go ahead and address it now. Phase levels. So we have aqueous, we just talked about, means dissolved in. If something is going to stay in a liquid form, you literally just put a lowercase l. If it's a gas, you're going to put a lowercase g in parentheses. And then if it's a solid, you'd put in a lowercase s to say it's a solid. And there are other phase labels besides this. For instance, sometimes we will talk about something, a particular solid. You'll write a down arrow and you'll put in parentheses. And this will mean that it is what we call a precipitate. And a precipitate is simply a solid that forms in a solution of something. Okay? That's really all that is. And sometimes you will see things in parentheses like CR for crystals, but we're not going to use that. That's used under specific circumstances, so don't worry about that one. All right, so those right there are the main ones that we will be using. All right, let's go ahead and clean this up a little bit so we can get right back to where we were. All right, you have to look at the reactants and think of them as ions. So remember, we have calcium and chloride ions in this first compound, and we have potassium, and we have phosphate ions. Now, what happens is this is a double replacement reaction. So the calcium and the potassium, the cation are switching. They are swapping. Once in solution, you have basically all of these ions that are floating around. And what happens is there are properties of these metals, depending on the charge, that affects whether or not they push, which one has, made, for lack of better words, a stronger push and pull. And we'll talk about that in more specifics in other lessons. I just want to stay focused on this one, on how to write these. So what happens, you see, is the potassium and the calcium swap. But what does not swap are the anions. Those stay the same. So we're going to come over here to this side, and I'm going to put the chloride ions right here, and I'm going to put the phosphate ions right here as well. Now we know that we see that the potassium is now over here with the chloride. So come over here and do this. And we know that the calcium is now over here with the phosphate, so I'm going to come over here and do this. Remember, everything we're doing right here is simply scratch work. Okay? Now, remember, everything that goes on this side, these are products. Sometimes there's one product, sometimes there's 4 products. It just depends on the reaction itself. Okay? So it says the chloride product. Well, that would refer to this right here. So what we do is we look at positive and negative 1. That equals 0. So we know that it's just going to be KCl. All right. And then, and remains in aqueous phase. So we now know about that whole AQ thing. So when I'm done, I'm going to go back and we'll put those labels there with this. All right. One thing at a time here. Then, while the phosphate compound formed is a powder, okay? So now we look at this and we go, well, there's a positive 2 and a negative 3. And what's common between 3 and 2 we know is 6. So that means if we had 3 calciums and we had 2 phosphates, then this compound would form. So I'm going to put a plus symbol, and so we need 3 calciums, so that's Ca3. And then we need 2 phosphates, right? So here is 1 phosphate. This is 1 phosphate. That's 1 polyatomic ion phosphate. Put parentheses around it, and then a 2. Now you have 2 polyatomic ions in this compound. There's 2 phosphates right there. Okay? So now let's go ahead and let's clean this up. Get that scratch work out of the way. Now let's worry about our phase labels again, right? Let's worry about our phase labels again. So it says calcium chloride and potassium phosphate are dissolved in water. So that lets us know that those are aqueous. So you come down here, sort of like a little subscript, and you put your phase labels aqueous, all right? It says the chloride product remains in aqueous phase. Well, this is the chloride product. It remains in aqueous phase, so we're going to come over here and put AQ. And while the phosphate compound is a powder, powder is a solid, so we could put an S. Now, here's where you may also see that instead of an S, what you could write is the down arrow right here and say that this is your precipitate. All right? This is your precipitate. This is the solid. All right, and there's another lesson where I'll demonstrate that and talk about that. But right now what we're looking at is this double replacement reaction, right? This is a double replacement reaction. And in this double replacement reaction, we saw that the two cations exchanged which anions they were with. Okay? Clean this up, get this out of the way. All right. We look at this and we ask ourselves, is this balanced or not balanced? Well, all you got to do is find one element that's not balanced on both sides of the reactant and product side. And once you do, the whole thing is unbalanced. All right, so we can see that there's one calcium on the reactant side, and over here we see 3 calciums. All right, we don't have to look at anything else. Automatically, this thing is not balanced. So here's how I recommend, here's a method to do this. What I like to do is draw a little table. Oops, that's not well done. I like to draw a table and then just sort of like draw a little dashed line so that you can separate your eyes between the reactant side versus the product side, okay? Now, if you think about this, you have 4 columns. You have this column, this column, this column, and this column. So now your eye is drawn to the fact that you've got 2 sides, the reactant side and the product side, and you have 4 columns total, all right? This is how I recommend you see this. Now what you do is you just come over here and you list out all of your elements. So we have calcium, there's chlorine, there's potassium, and when you have polyatomic ions, if the polyatomic ion on the reactant side does not break up and stays a polyatomic ion on the product side, you can count the polyatomic ion as if it were one element, like one type of element, because they are bonded together. So in this example, phosphate, the PO4, that's one phosphate and 4 oxygens that are chemically bonded, and we've had previous lessons like a Lewis structure. They are bonded that way, and they stay that way in the reaction. So for that purpose, for that reason, we can come over here and just list the phosphate as if it were just one single element anion, right? Just like chloride. Okay. Now what you do is you just list how many you've got. Calcium chloride, we see that there's 1 calcium, and we see that there are 2, we see that there are 2 chlorines. There's no potassiums, no phosphates, so we're just going to leave that blank. Go to the next compound, potassium phosphate, K3PO4, and we see that there are 3 potassiums, and there's only 1 phosphate. There's 1 PO4 in this entire thing. What you have to be able to see that that's just 1 phosphate in that compound. Okay. All right. Now I'll go to the product side, and potassium chloride, there's 1 potassium and there's 1 chlorine in there, right? 1 chloride ion on that. And then we come over here and we see that there are 3 calciums. There are 3 calciums in this, and there are 2 phosphates in that compound. Again, you need to be able to see that there's 2 phosphates there, all right, and 3 calciums. All right. So now that we've got this, here's the next thing that I recommend. we've got everything separated nice and neatly. On the left side is the reactants, the right side is the products. Excuse me, I needed a sip of coffee. Take a look and ask yourself, what is in balance and what is not in balance? Well, we see 1 calcium, 3 calciums, those aren't balanced. 2 chlorines, 1 chlorine, not balanced. 3 potassiums, 1 potassium, not balanced. 1 phosphate, 2 phosphates, not balanced. So nothing is in balance. Now at this point, it doesn't matter where you start. With practice, you'll begin to see patterns emerge very quickly, and you'll be able to do this at a much faster pace. Right now, whenever you're balancing an equation, just pick an element to balance. And remember, each of these right now has a coefficient of 1. Excuse me. There's a coefficient of 1 here. There's a coefficient of 1 here. There's a coefficient of 1, coefficient of 1. We don't write 1s, which is why they're not there. It's understood that there's a coefficient of 1 at the moment here, okay? So what we do is just pick an element. Well, we can see here that calcium on the reactant side, there's only 1, and 3 on the product side. Well, that's easy to do. If we just put a 3 here, 3 times 1 is 3, but that means 3 times all of this. So it's like distributive property, be 3 times this 1 calcium and 3 times these 2 chlorines. All right, so 3 times 2 is 6. All right, so now calciums are balanced. All right. Calciums are balanced. Chlorines, we have more on the reactant side than we had before, and that's fine. That's perfectly fine. So we ask ourselves, if there's 6 chlorines there and 1 on the product side, well, that's kind of easy because we know 6 times 1 is 6. Well, that's in balance. But that also means, so that's 6 times that, all of this, so that means it's 6 times this 1 as well, right? All right, let me back that up because I just want to get rid of that. 6 times this 1 here is 6, okay? Now, we look at this and we say, okay, wait a minute. There's 3 potassiums, 6 potassiums. That's a ratio of 1 to 2. 3 to 6 is the ratio of 1 to 2, which is also right here, 1 to 2. So even though the numbers are different, the ratios are the same, just like your math teachers have taught you, right? And so we ask ourselves, well, how could I change this 3 to become a 6? Well, that's easy. 2 times 3 is 6. And 2 times this 1 phosphate is 2. So now we've got 2 and 2, check. 6 and 6, check. 6 and 6, check. 3 and 3, still in check. This reaction is done. It is now balanced. So, in the end, the skeleton equation was what we originally wrote, where all the coefficients were 1. A skeleton equation being like the basic equation that just has the compounds there when we write it out. Now, it's the bare bones basic, which is why it's called a skeleton equation. Now, what we now know is that we have, so let's just say we're talking about individual molecules. There are later lessons where we know that we're talking about more than just molecules, but let's just keep it simple for right now. This basically says there's 3 molecules of calcium chloride plus 2 molecules of potassium phosphate produces, that's what the arrow means, 6 molecules of potassium chloride plus 1 molecule of calcium phosphate. All right, and that's it. This a little more complex than some of the earlier videos, but the only thing that makes it more complex is the fact that you have some subscripts, 3s and 4s and 2s all mixed together. It just looks a little busier, but once you get used to this, you'll realize that it doesn't matter what's there. It's all the same. You'll recognize the patterns. I would just recommend that you use a method like this to help you visualize what's going on. When you're dealing with coefficients that are smaller, eventually you won't need something like this. But there are reactions where you're going to see, you'll start seeing coefficients like 11 or 19, 7, 25, 16, 18, things like that. And when that happens, it gets a little busier. And a method like this, where you can show your work and see what's going on, I think is a good visual. It's a good tool to help you get from point A to point B, to help you get started and get finished with this thing. All right, so I promise you, if you use this tool, it'll work. And again, when you use it, if the element that you pick, you try to balance it out and it doesn't work for you and you get stuck, the good news is you just back up and start over again. It's just a little trial and error. Okay, so I hope this helped. Definitely work on your problem sets, check your answers, ask me questions. It's always great to learn with you. You take care, and I will see you in another lesson really, really soon. Bye.